Hey folks, I got two more rotational kinematic examples for you. In the previous video, we did three of them, so this will be 4 and 5. And in this one, just everything I've listed there is in radians and seconds. Okay, so alpha is not constant; it's equal to 4t radians per second squared. Omega naught is -3 radians per second, and theta naught is 20 radians. And what we're going to determine is what's the angular velocity of this particle as a function of time, and what's its angular displacement as a function of time. Okay, so we have non-constant acceleration, so we cannot use our shortcut equations for constant acceleration. So the two that I'm going to rely on here are omega is d theta dt, and alpha is d omega dt. Now, this is the kind of stuff we could have done way back in our first unit with linear kinematics. We didn't do it then because it's going to require integration, and if you're in calculus right now, you hadn't even touched integration yet. So, but now most of you have actually done integrals in your calculus class, and so what I'm about to do right now hopefully won't look completely foreign to you. Okay, so having said all that, okay, so how do we do this? So I'm going to start with omega, okay, and I'm going to use alpha equals d omega dt, and I'm going to get the d omega by itself. So d omega is alpha dt. And I want to get from d omega to omega. So what we're going to do is we're going to integrate both sides. All right. So we're going to do an integral on both sides. Now d omega is going to go from omega naught to whatever omega at whatever time I want. Okay. Now as I do this, for the most part in this course, we're always going to be doing definite integrals. So it's critical that you put limits on your integrals. Okay. Time, well, when we're at omega naught, that's a time of 0, and then we're going to go to some future time t. Okay. So those are our limits of our integral. Okay. Now I'm going to actually integrate. So this first, well, I'm going to do one more thing. I'm going to sub in my alpha term there. So I've got d omega from omega naught to some omega at some time later equals integral from 0 to t of alpha, which was given as 4t dt. Okay. Okay. So the left side of this equation, if you integrate d omega, you get omega, but you have to evaluate that from omega naught to omega sometime later. On the right side, we're integrating 4t, which is 2t squared, and we have to evaluate that from 0 to sometime later, t. Okay. And I'll continue this over here. So the left side simply becomes omega as a function of t minus omega naught. The right side simply becomes 2t squared. So omega as a function of time is equal to omega naught plus 2t squared. And we gave you a value for omega naught, which was -3. And so you can put -3 plus 2t squared. Okay, so that is omega as a function of time. Now, and then you can plug in anytime you want. You can figure out omega anytime you want. Okay, this idea of integrating, as the course moves on, we were going to do this more and more. So you might have to watch this a couple times. You might have to go back to it a few times, make sure you've written it down. But this idea of integrating two sides of an equation and having limits and so on is going to be absolutely important for us as we move on in the course. Okay. Now, we're going to do a similar thing to figure out theta as a function of time, and I'm going to use this relationship, and I'm going to get d theta by itself. So d theta, oops, sorry about that, d theta equals omega dt. Okay, and I've got omega. I just found that. So I'm going to integrate both sides. This will go from omega naught to omega at some time later okay? And time will go from 0 to t again, okay? So I'll go ahead and plug in my omega, or my expression for omega, which is -3 plus 2t squared. We're going to times that by dt, and we're going from 0 to t. Okay, so on the left side, this just becomes theta, and I have to evaluate that from theta naught to some time later. On the right side, we get an expression. We get -3t plus, it'd be 2t cubed over 3. So I'll just write it out that way, 2t cubed over 3. And I had to evaluate that expression from 0 to t, but that's pretty easy. On the left side, we just get theta as a function of time minus theta naught. On the right side, we get our -3t and then plus 2t cubed over 3. Okay, and then I gave you a theta naught in our work up here. That is 20. Okay, so we got theta as a function of time minus 20 equals 3t squared plus 2t cubed over 3. And if you get theta by itself, you've got your answer. You've got negative or positive 20 plus or minus, oops. Okay, this second term here, I messed this up. Let me fix this right there. That's -3t. Don't know what I was thinking. All right, so that should be minus 3t and then plus 2t cubed over 3. So that is theta as a function of time. Okay, so you can then find theta at any time you want by plugging in whatever time they ask you for. So that's an example using integration to solve for something. So in other words, we can go back and forth. We can use derivatives to get from theta to omega to alpha. And we can use integrals to get from alpha to omega to theta. Okay. All right. Now I got one more example for you. This one will be quicker. Let's see. Well, this is example 5 for me. And let's say I give you the following data. Let's say you're traveling in a circle. So here's a circle you're traveling in. And let's say you're right here at this moment. And let's say you're rotating counterclockwise, and we'll make that positive, keep it simple. And let's say I give you the following data. You start from rest, so omega naught is 0. And you have an angular acceleration of 2 radians per second squared. And the radius of the circle is 10 meters. Okay. When time equals 2 seconds, I want to determine the total linear acceleration of u. So what's the total linear acceleration? And that's critical to understand the difference there. Okay, well, you can have two types of linear acceleration. You can be speeding up or slowing down. That's our tangential linear acceleration. And you can have a radial linear acceleration. If you're going in a circle, you will have a radial linear acceleration. Well, in this case, we have both. The first one to find is AT, and that is exceptionally easy. That's just R times alpha. And I've given you R and alpha. R is 10 and alpha is 2, so this is 20 meters per second per second. So you are speeding up, and that's pretty rapid. For AR, okay, that is, there's two versions of that. There's V squared over R, or if you translate that, that's omega squared times R, okay? Now, I don't have V or omega, but I gave you enough information to figure it out. Now, this is a constant angular acceleration question, so I can just use omega final equals omega naught plus alpha t, and this would be 0 plus 2 times t, which is 2, so this would be 4. So omega final is 4. So this becomes 4 squared times the radius, which you get 160 meters per second, okay? Now, if the question just asked you for total linear acceleration and it didn't tell you anything about how to express it, and let's say this thing was here right now, Well, then I would just write it this way. It's negative 160 I hat plus 20 j hat meters per second per second. So that's how I would write it, okay? But they may also ask you to find the magnitude of the total linear acceleration, in which case you would just Pythag these two numbers. They may even ask you for an angle. So then in that case, you would, maybe here's your AT going up, and then here's your AR going left, and you could find the magnitude and you could find an angle in there. So that's an example of translating angular quantities to linear quantities. Okay. All right. I hope those two examples were helpful, and thank you very much.